How do you perform nonlinear dimensionality reduction? Imagine trying to understand a complex maze by only looking at a flat map. Sometimes, high-dimensional data is like that maze, full of twists and turns that are hard to see. Nonlinear dimensionality reduction helps us simplify these complicated data shapes into easier-to-understand forms. It's a way to take data that lives in many dimensions and find a lower-dimensional version that still keeps the important relationships. This is especially useful when data doesn't follow straight lines or flat planes, which is often the case with images, videos, or speech signals. The core idea behind nonlinear dimensionality reduction is called manifold learning. Think of the data as lying on a curved surface, called a manifold. These methods aim to unfold or flatten this surface so we can see the structure more clearly. To do this, they compare two types of distances: Euclidean distance, which is the straight line between 2 points, and geodesic distance, which is the shortest path along the curved surface. Geodesic distance captures the true relationship between points on a curved shape, making it very useful for these techniques. One popular method is called t-distributed stochastic neighbor embedding, or t-SNE. It works by converting similarities between points into probabilities, and then trying to keep those probabilities similar when reducing the data to 2 or 3 dimensions. This makes it great for visualizing clusters or groups within complex data. Another method is uniform manifold approximation and projection, or UMAP, which balances preserving local details and the overall structure of the data. It is faster and handles larger datasets better than some other techniques. Isomap, short for isometric mapping, uses geodesic distances to preserve the global shape of the data. It builds a graph connecting nearby points and calculates the shortest paths along this graph. This way, it keeps the overall structure intact. Laplacian Eigenmaps create a graph based on which points are close, then use mathematical properties called eigenvectors to map the data into fewer dimensions. Kernel principal component analysis, or Kernel PCA, extends the traditional PCA method by applying a kernel function to capture nonlinear relationships without heavy calculations. These techniques are used in many fields. In image processing, they help visualize high-dimensional pixel data, making it easier to spot patterns or anomalies. In natural language processing, they help understand relationships between documents or words. Speech processing also benefits from these methods by reducing the complexity of sound signals for analysis. When applying nonlinear dimensionality reduction, it's important to think about ethics. Reducing dimensions should not cause loss of important information or introduce bias. Choosing the right method depends on the data and what you want to learn. Trying different techniques and visualizing the results can help you find the best fit. These tools make complex data more accessible and help reveal hidden structures that might otherwise stay unseen.